Thanks for that. Okay, so I think I'll start. We're going to be recording this session, so hopefully anyone can view this later if they can't make it. So just a few bookkeeping things first. So yeah, if everyone keeps on mute, that's perfect. We'll probably leave the questions till the end, but if there's anything particularly important, then raise your hands. But if you can make your questions in the chat. This is the first talk really in a new series we're starting at the Catapult. So I'll talk a little bit about that. So the idea is really to talk about the value in energy data. So there's a lot of brilliant data sources becoming available, and there's a lot of brilliant research out there. This is sort of trying to connect some of that dots and say, you know, how do we bring that innovation, taking that data to the applications? So I'm really excited about the talk today. I've seen Kyri talk at a couple of webinar events, and I've seen some really interesting work she's been doing as part of the GRIFFIN Lab that she runs in the University of Colorado Boulder. So I'll give you a little introduction here. So Dr. Kyri Baker received her PhD in electrical and computer engineering from Carnegie Mellon University in 2014. And from 2015 to 2017, she worked at the National Renewable Energy Laboratory. And since 2017, she's been assistant professor at the University of Colorado Boulder and is fellow of the Research and Sustainable Energy Institute. Her research focuses on renewable energy integration by changing the way electrical power grids operate. In particular, she develops computationally efficient optimization and learning algorithms for energy systems ranging from building level assets to transmission grids. So I'm very excited to introduce her. So please take it away.
Thank you, Steve. Okay, let me share my screen successfully again. All right, I'm going to assume that that is properly shared. Please let me know if it's not. So in this talk today, I'll sort of be talking about some really, really recent areas of work that me and my team have been doing, basically harnessing data to speed up power systems optimization problems. So before I do that, I would just like to thank all the members of the GRIFFIN Lab who work on a variety of topics from energy markets to security constrained optimal power flow. One of my postdocs actually from the UK. She did her PhD at Oxford, and she's currently in Boulder, loving Boulder apparently. So thank you to my team and everybody who's supported this research. I thought I'd show a little image of the US grid here. So on the left-hand side, you see the transmission lines, the high voltage transmission lines, 138 kV. And on the right-hand side, you see all of the power plants that are large enough to be mapped by the Energy Information Administration. So the US grid is actually broken up into 3 AC grids. If you're not familiar, there's a Western AC grid and Eastern AC grid. And Texas is actually its own AC grid because, you know, Texas has to do its own thing. That's actually the reason they would like to not be overseen by the Federal Energy Regulatory Commission. So that by not having AC connections to other states, they don't have to follow the same interconnection rules. So this has sort of resulted in Texas installing a lot of wind, actually significantly more wind than any other state in the US, because they don't have this long procedure of having to go through all this paperwork. So the right-hand side, obviously, you can see that the power plants cluster around population centers, so the West Coast and the East Coast. But generally, it's a very, very complicated system. This is a very large country, and it has a lot of different resources that we have to coordinate in real time. So, and this is, a layout of most modern power grids. We'll have the power plants, we'll step up the voltage for high voltage transmission. Large customers like factories, manufacturing facilities will connect directly to that high voltage line, 3-phase line. We'll step down the voltage, and then the smaller customers, like perhaps smaller manufacturing facilities, commercial buildings, and residential buildings, will get the smaller voltage. And traditionally, we have to have the supply side and the demand side balanced roughly at all times to maintain the AC frequency at 60 hertz. So 60 cycles per second, 60 times a second, that AC wave is going up and down. So before we started installing distributed energy resources, this was a relatively standard practice. You would have the power plants perform this droop control that adjusts their power output slightly to maintain the system frequency at 60 hertz. But now we're getting a sort of change in this paradigm that's requiring us to change the way that the supply side operates. And that's what I'm going to be talking about today, is what do we need in this transition. So previously, this is what I like to call the orchestra. So we had these large centralized players that are responsible for coordinating the 3 AC grids and areas within those AC grids. So here you can see ERCOT, that's the Texas AC grid, not all of Texas, but most of Texas. You still have DC lines that are connecting ERCOT to the rest of the US and to Mexico. Here's the Western interconnection, and here's the Eastern interconnection. And within there, you have independent system operators, we call them ISOs. I know from my postdoc you call them TSOs, that balance supply and demand in real time. And they sort of coordinate the participation of the generators to adjust their output to balance the frequency at 60 hertz. So this was very centralized. The demand was sort of taken as, you know, some external input. They didn't really communicate with most of the loads. They were just sort of like, give me your power consumption and we'll adjust. And so this was the orchestra. This is a central coordinator coordinating all these pieces to work together. So what's happening now? So the distributed energy resources, or DERs, are being installed at increasing rates every year. So DERs can include things like distributed solar panels, home batteries like this Tesla Powerwall, even in some cases electric vehicles. We also, FERC just passed an order, some of you may have heard of it, it's called 2222 or maybe 2222, that said that distributed energy resources can now bid into the wholesale market. So if you want to work with an aggregator and have your Tesla Powerwall provide grid resources, then there's going to be a path for you to do that. So the grid wasn't constructed, or initially the operational algorithms weren't designed to account for all of this controllable distributed resources. And then this also includes things like, you know, there's an increasing number of microgrids, there's an increasing number of demand response programs and initiatives and energy efficiency measures, you know, teaching people and providing incentives for them to upgrade to LED lighting, for them to weatherize their house, and so on. So what is going on with this transition? Well, this is what I call the jam band, which means there's not going to be a centralized orchestra conductor, you know, telling everybody when to be in sync with each other. There's going to be a bunch of different players, a guitarist, a bassist, a drummer, and they're all going to have to, you know, just jam and then find the groove together and figure out how to work together in real time. So this is something that, you know, can end up sounding really good, but it takes us a while to get to that groove. It's not just like we know what to play ahead of time. We have the sheet music, we have somebody synchronizing us. We need to work together in this distributed fashion. So this is causing a big challenge for the grid. On one hand, there's a bunch of resources that the grid can now use, but on the other hand, there's less visibility and direct control over those resources. So why can't we just operate the grid on this 15-minute economic dispatch scale that we've been doing so far? So what we have been doing so far is generally the real physics of the grid are extremely challenging to optimize over on this 15-minute scale or even shorter. So what's been done since, you know, the 80s or maybe even earlier is we linearize the dynamics of the grid, and we use those linear models to determine what power plant should be generating and what set points the generator should be at. We assume that these power plants are controllable, they're dispatchable, they're generally not uncertain. If the gas plant says it can output 20 megawatts, it's probably going to be able to output 20 megawatts. And we assume that the load side was relatively slow moving. So traditionally, we had this very similar load pattern for decades, and that's only changing in the past 10 years or so because of these distributed energy resources. It's also changing a lot because of COVID as well. We're getting different load patterns. So why can't we use these anymore? What is the point of this talk? So the point is, a lot of these approximations that work decently well in practice, for the 80s through the 2010s, are based on assumptions that might not hold anymore. So the DC optimal power flow, if you're familiar with it, assumes that the lines are lossless. It assumes that all the voltage magnitudes are the same. It assumes that the phase angle differences between neighboring nodes is the same. It assumes there's no reactive power modeling. So a lot of these things are changing because the grid is changing. We're now getting controllable assets at low voltage levels, which inherently have higher losses. So we can't always have controllable assets. We're going to have large-scale solar plants or even distributed solar plants that are introducing uncertainty into the system. They can only curtail in one direction. They can't dispatch in the same range that traditional power plants can. And because of all these new loads, electric vehicles, batteries, different grid responsive devices like thermostats, the variability is increasing in net load in the grid. So we have to deal with increased uncertainty, variability, maybe our assumptions don't hold anymore. It's going to get harder and harder for centralized grid operators to optimize the assets over this very, very large system. And one big example of that, which I'm sure you're all familiar with, is the duck curve, which is a huge problem in California and Hawaii and becoming an increasing problem in other states as well. So this was from last year, almost exactly 1 year ago. And generally, this is what the demand looks like in the CAISO region, the California Independent System Operator region. So we have this dip in the morning, it's the middle of the night. People are not really consuming electricity. We have a huge peak when people start getting up. They start turning on electric kettles, cooking breakfast, turning on TVs and radios. There's a dip in the middle of the day because when people go into commercial buildings, there's a lot more density of people packed into one building that's generally much more energy efficient than residential buildings. So that's why there's a dip. And then at the end, when they come home, they turn on TVs, they start cooking on the electric range, and the demand spikes again. So California has been really aggressive with installing solar. And this is, again, last year, and it's even increased. The problem has even increased more this year. So what happens is when the sun rises, of course, we get this dip in net demand. The net demand is what the remainder of the power plants have to make up for. So the solar energy is, really, really generating a lot in the middle of the day when it's really sunny in California. And then as the sun sets, we get this sharp ramp upwards. And of course, this is the canonical duck curve because it looks somewhat like a duck. And in the problem with the duck curve, and the problem that California is facing and Hawaii is really facing, is that some of these ramps are really challenging for traditional power plants to account for. Some of the power plants can't change their output that fast. They weren't meant to. They weren't built that way. They weren't designed that way. And some of them might even have to shut off for a few hours in the middle of the day. So some nuclear plants, because of safety regulations and just because they need to cool down, can take up to 3 weeks to shut down and start back up. So we can't just be turning on and off these large energy resources as we want to. So we need to start dealing with all of these new problems in a dynamic and distributed way. So what should we do? So on the right here, here's a little power system, I think from Power World, the software. And ideally, it would be perfect if we could start optimizing the grid using this high fidelity physics-based model that has to model every line, every bus, every generator, every transformer with high enough fidelity that it models the actual physics of the grid. But this model is highly nonlinear, it's non-convex. It results in a really, really difficult optimization problem, especially over large systems. So we've traditionally not been able to use it for real-time operation. But as I said before, we're needing to use a real high fidelity model because all these assets are introducing all this uncertainty and variability. So how can we optimize this power system as grid operators for real-time operation under these changing, fast fluctuating conditions? So my theory is that what are we missing? What are we doing? What could we be doing right now that we haven't been doing in the 70s and 80s? And what we're not doing is we're not using enough of the data and knowledge that has been gained over those decades in order to operate the system better. So we do use data in the grid. We use it to predict for when we're going to have strain on the system. We use it to predict when we should upgrade certain components. Data is really used for planning and planning for upgrades and additional capacity additions. But can we actually use this data during operation, during real-time operation? Can we teach these algorithms to use previous knowledge? So the main idea behind why we haven't done this so far is because we've been collecting the data, but we don't know exactly what to do with it for operations. So that's where my group's research comes in. And the main idea behind this research is that we want to obtain the solution to this complex optimization problem without solving that AC optimal power flow problem. So AC optimal power flow is sort of the ground truth for determining what settings the power plant should be at to optimize for cost. And there's different variations. You can optimize for carbon emissions. You can optimize for water consumption of the power plants. But the traditional one that the markets solve is optimizing for cost. So this is not just applicable to large grids. You could also have this, let's say I have a limited computing resource that's a distributed energy resource. Let's say it's a thermostat or it's an inverter. What if these guys want to optimize their output? What if they want to communicate with their neighbors and determine how to maintain voltage within a distribution grid? These AC optimal power flow problems are extremely challenging to solve in real time. Optimizing is hard. So could we use data to avoid optimizing? So billions of dollars are lost annually due to suboptimalities in optimal power flow because we're using these linear models to operate these systems. So there must be some way where we can still solve this problem quickly. We can determine how to operate the system in a quick way, but we don't have to sacrifice as much optimality as we do with these linear models like DC optimal power flow. So the current paradigm for solving the actual AC optimal power flow goes like this. So we have to use some solver, some off the shelf, maybe like Gurobi or Cplex or IPOpt or something. Every system operator has their own software package that they use. Sometimes it's PowerWorld or PSSE or some other ones. So you get some initial guess for warm starting the optimization problem. It might not converge when you try to obtain the solution to the ACOPF, but while the solver is iterating, it has to, probably invert some matrices, tune some parameters, iterate for a while. It might not solve because this is a non-convex problem. If it didn't converge, you go back to the start, you try a different initial guess, or you try something else. Eventually, you'll obtain the optimal solution, the one that uses the real physics of the system. So this process is really hard, which is why grid operators don't do AC optimal power flow on fast timescales. So we're doing this potentially hundreds of times a day for years. Can we use all those historical runs to get this paradigm to be faster? So here's a quote from this paper just saying that the volume of data generated has now grown tremendously. We have a lot of sensors throughout the grid. We're installing smart meters locally, but a lot of this data is not logged or saved because grid operators don't know what the use for the data is. So the proposed paradigm is we have all these historical times that we got a successful optimal solution from this method. Let's train a model to learn how to go from this part to this part without getting into this yellow block. So every time the load changes, you input that into the trained model, which in my case is a neural network. It performs inference, which is extremely fast. There's no complicated layers in this neural network. And then you obtain something that's close to the true optimal solution. And as I'll show you in the results section, this neural network can actually really model and approximate the full ACOPF problem with pretty small optimality gaps. So what does this mean? It means that instead of using those droop curves, instead of using those heuristic power adjustments to maintain frequency, we can instead actually pursue optimality in real time. Okay, so every time I present this, there's always a lot of pushback from traditional power systems people that don't want to use a black box, because a neural network is essentially a black box, especially the big ones. So does this actually work? Should we put all the physics into this black box and then actually obey the output and implement that in a real system? So a few papers in this area have come out that are pretty convincing. So this top one was solving a security constrained DCOPF problem, which is a very complex problem that includes potentially integer variables, discrete changes. And they were able to solve this optimal power flow problem on an 1800 bus network in less than 2 seconds. And this was way closer than, a lot of the heuristics we use right now. One of my papers, in collaboration with one of my colleagues at the National Renewable Energy Lab, obtained feasible ACOPF solutions, slightly suboptimal, but a lot more optimal than DCOPF, 6 to 20 times faster. So this was a network that was trained on a laptop. It wasn't that complicated of an architecture, and it was still able to solve this really complicated problem by using historical data and saying, hey, the load was this at this time, the optimal solution should be this, let's learn this pattern. And we were able to do that much faster. Some of these ACOPF problems are really challenging to solve. Let's say you're close to a point of voltage collapse, or you're close to the point where all your generators are going to be maxed out, you're running out of capacity. These edge cases can be hard for a neural network to learn unless they were included in the training set. But this group recently used this, it's called the Helm method, the holomorphic embedded load flow method, to ensure that they can always get a solution. So they embedded this Helm method into the neural network, and they ensured, like, even on these edge cases, we're going to get something that's physically feasible. It might not be optimal, but the system will be stable. It will be physically feasible. So using a neural network to map loads to optimal generation set points is something that's really exciting, because we can actually find a use for that data, and we can solve this problem that we're really needing to solve on a faster time scale because of all this increased uncertainty and all these different assets that are being added to the grid. So why is it powerful? Why does a neural network work so well for this problem? So here's we only used a 3-layer neural network, but this is a nice complicated figure. So you input the loads. That's what's changing in the system generally, and this could be the net load, the load minus the renewable energy generation. And then it outputs the settings that the generator should be at, for example. So when we try to approximate these AC power flow equations, these nonlinear physics of the system, linearizing implicitly makes us lose a lot of information. There's no way to create a linear function that represents the non-convex space that the AC power flow equations have. But neural networks do a better job of representing these very complex relationships between load and optimal power generation. So it is still an approximation. There's ways that you can embed the actual ACOPF physics into the neural network, but that slows it down significantly. It is still an approximation. We are still fitting a neural network to this optimization problem, but it's really good. It's at the level where we're probably willing to make a sacrifice, 0.1% gap between that and the real solution. So feasibility is a really big challenge, even more so than optimality. Feasibility means that we're providing a solution that's physically realizable. It satisfies all of the constraints. It does a good job of representing physics, but maybe the system's operating slightly more expensive than it should. So when I first got into this area, my first question was, how do we use a neural network to speed up OPF while maintaining feasibility? So in that 3-block diagram, I was looking at how can we do a better warm start or a better initial guess to a commercial solver. So I first looked at random forests because those were easier for me to implement when I was beginning in this area. And you can see that when we input, the traditional, let's say using a DCOPF as a warm start, it takes more iterations to converge than if we use a learned warm start. meaning that we're putting the initial point closer to the ACOPF solution, and then it just has to iterate a little bit to get to the full solution. So the warm start, that worked decently well, but we're still not extremely fast. You know, it's maybe a few seconds faster in this particular case by using the learned warm start. We really want to revolutionize the way this problem is solved, not just make these minor increments. So actually, I'm going to skip this part. All right, so the second idea was maybe we can emulate how these software packages work themselves. So these solvers work really well. In fact, the map power interior point solver, the MIP solver, was specifically designed for AC optimal power flow problems. And this is a free solver in MATLAB. MATLAB's not free, but the solver code is free. So the idea here was, okay, let's try to replace every iteration in this interior point solver with a neural network. So no matrix inversions, no large matrix factorizations, no like tuning the parameters to get it to converge. Let's just try to approximate that little iteration. And what that means is sort of, let's say we're, you know, iterating and trying to find where this root crosses the x-axis. So what happens is you provide an initial guess, it'll calculate a gradient, it'll keep iterating and calculating gradients. This is not exactly how it works, but roughly, until you reach the optimal solution. So instead of going directly from initial point to optimal solution, my idea was, let's just learn these baby steps towards the optimal and have the neural network learn the baby steps and emulate those until we get to the optimal solution. So every pass through here emulates one of those little gradient steps. So you can see this is kind of a simplified recurrent neural network because we input the loads, we input the candidate optimal solution, it goes through the neural network, then we output what we think is the next step, and then we repeat this process until x of k and x of k plus 1 get really, really close to each other, which can be the termination criteria of the normal algorithm as well. So let's see if we can emulate the solver. So just as another note, I emulated the solver using a Newton-Raphson algorithm, which is one of the most popular algorithms to solve AC optimal power flow. And the algorithm, the Newton-Raphson algorithm, can basically be written like this. You have some candidate optimal solution, you apply some function f, and then you get your next candidate optimal solution x of k plus 1. So the f in the Newton-Raphson sense is traditionally a matrix inversion and then some multiplications. In the neural network sense, that f is a very easy to evaluate function compositions and multiplications and evaluations of sigmoid functions and tan h functions and linear functions. So doing this forward pass is really, really fast, and meaning this f for the neural network is much easier to evaluate. So I trained it to learn these iterations, to iterate sloppily towards the optimal solution. Let's see how well it did. Okay, so here's just on the left-hand side is the 30-bus system, IEEE 30-bus system, which is a small system. You can already solve AC optimal power flow in real time, but it has it easier to it's easier to visualize. So here's the output of 6 different power plants in the IEEE 30-bus system. I just plotted 200 test scenarios here on the x-axis for randomly generated loads in the network. The colored lines are the neural network's predicted optimal solution, and the black dashed line is the true optimal solution. And you can see that it's really, really close. And in some generators, it has a really easy time learning what they should produce versus the other generators. So this one up here is the slack bus. That one, it had a very challenging time predicting for some reason, but the other generators, it did a really good job of predicting their optimal output. And let's take a look at some of the larger networks. So maybe the 1354 bus network. So in this bottom table, I have the error, so the mean absolute error and the mean absolute percentage error. You can see that for voltage, it does a pretty good job predicting what the optimal voltages should be. The active power, it's a little bit high in this network, but if you look at the overall generation capacity, it's not that much. It's okay if you're off by a little bit as long as the load is satisfied. And the cost function in the largest case is 1% more expensive than the true optimal. But if you look at DCOPF, which is what grid operators are currently using, you often get a much larger cost percentage difference, meaning that we're operating these markets and these generators are outputting power at a sort of an inefficient way. What does this allow us to do? So what it allows us to do is provide optimal solutions in real time, rather than using automatic generation control or some other method to adjust output from the generators. So here is the 500 bus system. I simulated it for 30 seconds and I said, okay, let's try to track true optimal solutions, meaning this blue line, in real time. Let's see if the learning-based method can provide optimal solutions on a second level. So you can see that the black dashed line is the true optimal. You can see that the learning-based method tracks this solution pretty well. You get some gaps where it's slightly a different generation dispatch, but it does a really good job of providing optimal solutions in less than a second to these generators. Now, map power, which is a really good solver for AC optimal power flow, takes a few seconds to solve. And so what you do is you get these generation set points that are out of date after a couple seconds. The load is changing on a crazy scale in some of these networks because of all these distributed energy resources. You get solar panels introducing seconds level fluctuations in the power supply. So by the time map power has said, oh, here's your optimal solution, generators, and the generators hold that set point, it's already out of date in a few seconds. This is, of course, an extreme example. The generators would have a mechanism, AGC, to adjust their output slightly, but it would still be more heuristic than the learning-based solution. Okay, so does this actually converge? So with Newton-Raphson, there's no guarantee that it converges. With the learning-based method, there's also no guarantee that it will converge, but in every situation I tried, it does converge. And by converge, I mean as you're going through the neural network multiple times, eventually your input starts to equal your output. So you can see with this large system, the 1354 bus, the map power solves it in a couple to convergence in a couple iterations. The learning-based method, because the iterations are approximate, takes longer. It takes a lot more iterations, takes 15 iterations. But each one of the learning-based method iterations, which is just performing inference, is a couple milliseconds, whereas every iteration of map power's Newton-Raphson algorithm is a second or two. So when we look at how much speed up we get, even in the large network, we're getting 22 times faster operational times. So if we were only able to solve ACOPF using a traditional method every 10 minutes or something, we're now able to solve it in less than a minute with this learning-based method. Okay, so the previous results that I showed you don't ensure that the AC power flow constraints are satisfied. Again, they're just iterating towards an optimal or an approximate optimal. So what can we do to ensure that physics holds when we provide these generator set points? So what we do is, after this has converged, we send a subset of those predicted variables. So for generator buses, we send the PG and the V. For other buses, for the slack bus, we send the voltage, magnitude, and angle. Depends on what type of bus it is. But we send those to a power flow solver. And it's important here to note that this is not an optimal power flow solver. There's no optimization problem being solved in this whole thing. This is simply a nonlinear equation solver. Power flow is just a set of nonlinear equations. So we've gotten the neural network to provide these generator set points that we think are optimal. We send it to a power flow solver to get feasible voltages to make sure that everything's operating safely. This affects optimality a little bit because it's going to have to make a little bit of adjustments to make sure that the physics holds, but it's generally way closer to the optimal solution than DCOPF. And let's actually look at that. I've been, talking trash about DCOPF this whole time, So what's the benefit with DCOPF? Let's go directly to this 1354 bus system. So on this column, I have the average time to solve, I think, 1,000 different loading scenarios. And I have the percent of the time that it was able to solve that. Because if you've ever run ACOPF, you've probably encountered cases where the solver can't find a solution. So I tried 3 different versions of ACOPF. I tried giving it a flat start, so all the voltage magnitudes are 1 and the angles are 0. I tried giving it a warm start with a DCOPF solution. I tried to give it a power flow solution, so really close. Here's the neural network, and here's DCOPF. Okay, so the average solution time for the flat start is 20 seconds for this network. It's pretty long. For the power flow start, we get the fastest time. It solves in 10 seconds because we're closer to the optimal solution. For the neural network, it's just so fast. It's so hard to beat anything. It's, you know, a fraction of a second. And another benefit with the neural network is because we're not dealing with these singular matrix inversions or ill-conditioned matrices, and when we're traditionally solving an optimization problem, we get a much higher percent solve success with the neural network. And the 2% here that failed was actually in the power flow solver, not in the neural network, because there's no failing in the neural network. DCOPF is actually even slower than the neural network. That's because we're still having to solve an optimization problem. We're still taking gradients. We're still iterating towards the optimal. It's still slower. Of course, it satisfies, you know, it solves 100% of the time. It's a linear or convex program. You know, as long as there's a feasible point, it's going to find a solution. But it's even slower than the neural network. So you can see that for the 500 bus system, the neural network and DCOPF solve in the same amount of time. This one was a bit easier network to solve. Nobody had a problem here. But the take home here is sort of the neural network can provide a really strong trade-off between providing a solution and providing that solution quickly. And I compare with DCOPF here just because that's what a lot of grid operators in the US currently use. How optimal is it? So we have these locational marginal price-based markets. So in all of those ISOs, those independent system operators, people bid into the market clears, and then the market participants get paid a certain price. And in a lot of these markets, that price is the locational marginal price. So what is the cost to deliver energy to your current location? That's the price they get paid. So DCOPF is used to run these markets. It's used partially to calculate LMPs. In some markets, they don't even use OPF. They use what's called power transfer distribution factors, which is another heuristic. But the reason I include DC here for the pricing is because this is currently accepted in industry. So you can see the average optimality gap, meaning between the true price, the true ACOPF solution, and what the DCOPF is providing. It can get pretty big. It can get up to 5% on average and 16% in the worst case. We're talking millions of dollars here lost due to these OPF inefficiencies. The neural network has a much better optimality gap, meaning it's getting solutions that are closer to the true optimal. So in some of these cases, it's just negligible, 0.09% in the largest network average optimality gap. That's, for most power plants, it's probably acceptable. The 500 bus has a larger gap because it's not necessarily the size of the network that makes this a challenging optimization problem. It's also the characteristics of the network. So it's hard to say that the 1354 bus is harder optimization problem. It's not necessarily true. So the point of this slide is that we're trying to minimize market inefficiencies with the learning-based method as well. Okay, so this is a radar chart and it looks terrible. It's probably the most lopsided one you've ever seen, but it allows us to look at these 3 different choices for operating the grid. We could continue to use DCOPF, we could finally move to the true ACOPF, or we could try to use a data-driven solution. We could try to leverage all these historical runs or runs that we've generated offline on a slow time scale and train to this black box model. So on this axis of the radar plot, we have the average optimality gap. So for DCOPF, it's big because we're solving this linear system of equations. For ACOPF, it's small because we're solving the actual, the actual problem. The percent failed solves. So this could be really scary if you're operating a real-time system and your solver just spits out, couldn't find a solution, or a singular matrix encountered. ACOPF does the worst here because it's a non-convex optimization problem. There's no guarantee that you're going to be able to solve it. And then on this axis here, we have the time. So I've normalized the ACOPF to be 1, and then we look at the DCOPF and the neural network. So right here in the center, this little triangle is the neural network's performance. It has a pretty small optimality gap, has a very small solve time, and it also has a very small percent failed solves. So overall, if you're looking for the best trade-off between all of these characteristics, it's probably best to go with this data-driven method. Again, assuming the data is good, there's no corruption, and that we have enough data. Okay, there are a lot of downsides to this method. I'm not going to ignore them. One downside is that when you train the machine learning model, it's trained for a particular topology. It's learning the OPF solutions based on the existing layout of the grid, based on everything it's seen in the past. And if you change anything about what it will see in the future, it's going to be totally off. So if you have a line that's removed, or you replace a transformer, or a power plant kicks online that you didn't have in the training data, you're going to need a totally separate model. Now, this is an active area of research. How can we add and remove power systems components and have the neural network capture those additions? But currently, nobody's solved that. There's no guarantees for feasibility. So even the one that I showed you where it puts it into a power flow solver, there's no guarantee that power flow solver is going to correctly solve and find a feasible point. And then, of course, the same problems exist with any machine learning model. If we have not enough training data, if we don't know what we're doing and we're just throwing everything in TensorFlow and seeing what works, in practice, this might be really, really bad. Class imbalance if you're doing stuff like classifying, unit commitment or something with a neural network. So all the same problems exist here. It's not a silver bullet solution. Okay, so I just want to leave you with, hopefully thinking that a lot of this data generated by the power system isn't just used for planning. It's not just used for upgrades, but it can also be used for real-time system operation. And I'd be super happy to take any criticisms or questions that you may have.
Thank you very much, Kyri. That was brilliant. Yeah, so if you want to either type your questions in the chat, or if you put your hand up, you can, when I call you out, you can unmute yourself. I have got a couple of questions myself, actually. So I suppose talking about the data they're not really using to do this sort of thing. When you've spoke to SOs, TSOs about these methods, what sort of reaction or discussions have you had?
The biggest issue is that they don't trust a black box. So the solution that I provided, where it spits out the neural network solves, but then it goes to a power flow solver, that was kind of my best workaround for something they might trust. But there's so much built into the practice of operating these ISOs right now that relies on human intervention and human know-how. I talked to an operator in Texas that said that, oh, I just know which lines are going to get congested, and I just know which ones to look out for. So I see if I need to call up this power plant to tell them to ramp up. So it's a combination of, it's scary to think you're going to be replaced by a machine, and also we don't trust black box models.
Right. Okay. Do you see that changing, maybe?
I hope so. I'm not sure, though. Another problem is the same 3 companies provide all the software that most of the ISOs use here. So it's like probably the best bet to get one of these algorithms in production would be to work with one of those software companies like Siemens, to have a feature that integrates in so the grid operators trust it more, maybe.
And I think Ridoy had his hand up. I don't know if it's gone down now, unless you have.
Yeah, just a quick question. Kyri, thank you very much for the presentation. Indeed, very interesting. Just wanted to check quickly one thing. When you compared the AC power flow did you also compare it with the second order conic problem? I know that has certain advantages. Definitely doesn't overcome all the difficulties in terms of number of iterations and the gradients. But I was wondering if you checked that.
That's a great question. One of my PhD students is actually working on that right now, comparing second order cone with SDP, with DC, with AC, because the second order cone has the benefit that it's a convex problem and that generally its optimality gap is really low. And it is faster, but it's still way slower than the neural network.
Okay.
So we're trying to quantify those.
Okay. Thanks.
I'll just, David's written in the comments and I'll get to the hands again. David's asked, how dependent is a neural network approach on the past conditions that have been solved previously? So how often does the neural network require retraining as the demand generation pattern develops, as opposed to topology changes? Or is it agnostic to real past behavior? And how expensive is retraining?
Good question. I think this would be best if I actually drew something. So this is the most simplified representation of the ACOPF feasible region that I can draw, but it represents the non-convexity of the feasible region. So generally, the points you're going to generate during training are basically, you're trying to span all of the possible loadings in the network and then use an off-the-shelf solver to slowly solve these different OPF problems. So most of the solutions are going to be in the interior of these feasible regions. And roughly the points that are in the interior, the neural network can learn really well. It can learn points in between them. The problem exists when we start approaching the boundary. The error can be really large and it can start producing infeasible solutions because the neural network doesn't understand this boundary. Sometimes it'll produce a solution that's in between two actual feasible points and you'll get something infeasible. So the retraining kind of happens when this boundary changes. And that's really hard to know when that happens in practice, but training it is not bad. I did it on my laptop locally in a day. So it's sort of like you would probably want to do it every few months or something, I would guess.
Great, thanks. Tibin, you have a question.
Yes, indeed. Thanks, Stephen. And thanks, Kyri. That's an interesting presentation. You touched upon the odds and the pros and cons as well. So you always covered that very pretty well. I mean, I was wondering, can you put any numbers, again, is not using or the lost value of not using this concept? For instance, if going with the DCOPF and if you move to a ACOPF/NNM based kind of approach, what's the lost value of operators not being moving from the traditional DCOPF to that? And the second question, just to summarize, obviously you mentioned there is no guarantee and the effect can be disastrous. So as an operator, I mean, I work with few operators, so there's always a hesitancy in taking up this kind of approach on board and replace with the humane, decision-making approach. So what is the next, ideal step to kind of bridge that gap? I mean, you already answered, Stephen, but kind of, it's next an ideal step or approach you suggest to kind of reduce that gap?
Yeah, that is exactly what I'm trying to figure out right now. Wait, what was your first question again? I'm trying to answer that one first.
It's the lost value in terms of monetary value, not using or adapting to this approach you propose compared to the old one.
Yeah, that one. So that FERC report that I cited in one of the earlier slides estimated that by using DCOPF instead of ACOPF, billions of dollars are lost annually. And this is because of that optimality gap. Essentially, we're choosing suboptimal power plants to produce electricity. So we're going to have this, summing every 15 minutes of money that's lost in the market. So that doesn't even look at reliability. There's probably also reliability issues that we could solve, but billions of dollars for just changing an algorithm is pretty significant. And then to your second question, that's exactly what we're trying to work on right now. I'm calling it sort of letting the operators have confidence in these solutions. And one of the ways that I think we would be able to do that is by creating a hybrid approach where, for example, we just learn a starting point for their ACOPF solver. We could still shave off some time with that and provide some better reliability. Because if you have a bad starting point to the algorithm, it might diverge or it might not converge to the right point. So integrating that in a hybrid approach, I think, is the best way. What I showed today is sort of like the best, the totally black box method, which probably isn't realistic right now.
Right, thanks.
And Hridoy, you have another question?
Yeah, just quick thoughts that came up when you were discussing, basically. One is, I think it would, so you said that when comparing the three options, 30 bus, 500 bus, and 1354 buses, you said that, and I can totally understand that it's not the number of buses, but it could be the feature of the network that determines how complex it is to solve that power flow. Mm-hmm. Now, would it be useful to maybe determine some categories or features of those networks that make that power flow not easily solvable, so that when we start seeing those features, we know that certain solvers will start to fall apart, so we might better direct our efforts in some other solvers. And that's one. And the other thing, when you were talking about the hybrid approach, I was thinking, can we have and here it could be a very stupid idea. I'm just thinking out of what we just discussed. Something, as you said, hybrid approach, but with a sort of, based on the optimal confidence interval that you want. So depending on the confidence interval that you set, you translate to one, you basically move between two or more approaches, depending on the confidence interval you set, and you move like continuously. I'm just thinking, I'm not sure if that is even feasible.
Yeah, that's a really cool idea, because, okay, so the first point about the determining the features of the network being challenging, my first thought was, oh yeah, it's how the size of the feasible region, but it's actually more like the shape, because it could be one line that is, and we're seeing this with my project with my postdoc, it could just be a couple lines in the system that are really constrained that make it difficult to find a solution. Yeah. So determining what features make it difficult is a really interesting problem. You probably have to generate a bunch of different loading scenarios and try to come up with some kind of pattern, but that's cool. And then the second point, I like that, because if, like I was saying, if you're inside the interior of the feasible region, if you're within like a normal operating scenario, the neural network does really well. It's just when you're towards the edge, or you're towards these the voltage constraints being binding, that it starts producing these funky situations. So maybe there's a way that we can flag, based on this load, we have low confidence, so let's run the solver. Yeah.
Thank you.
Great. Thank you, Hridoy. Jake Verma's got a question. What are the common strange non-technical arguments against using a more informed approach? We found the network operators have very low digital literacy, which makes it hard to implement new techniques, as it causes a high aversion to risk. Is this the same for the networks you've worked with?
My theory on this is that I've encountered some distribution system operators or some of the microgrids in Colorado that they're actually pretty happy to try some stuff, but the algorithms I've developed are only for transmission grids. I think when it's a smaller system, they're more likely to be willing to try it, because they can always override. Some of the microgrids in rural Colorado are like, 22 houses or something. So it's okay if we mess up something for a little bit. So that's, I think, where I'm going to go with this, is if I want it actually implemented as distribution grids. Some of the other arguments, though, I've heard we can't change the way the markets work because everyone's used to getting X payments and everyone's used to the price being calculated like this, and all these different firms and generation companies are expecting the grid to operate in this way. So I think that's like a policy change. You can't just change the way the market calculates prices without, maybe a transition period. I don't know how to get around that one.
Interesting, thank you. Maria asks, hydrogen production electrolyzers and storage integrated with electricity could potentially be used to counteract the effect of renewable production intermittency. Would this simplify or complicate the electricity grid stability and optimization?
I think probably it would make it better because that's essentially a flexible load. So again, this is the trade-off with the orchestra becoming a jam band, is there are more controllable assets. So on one hand, you know, we have more flexibility to balance supply and demand, but on the other hand, this problem gets larger and more complicated. But something like, you know, a large hydrogen production facility or some other kind of chemical plant that's not just a DER could be really beneficial to the grid, I think.
Thanks very much. I have a quick question, actually. I was thinking about back to the question from David about the sort of previous history you've seen. I imagine then, maybe you've sort of answered this, that some of the more complicated problems are those edge cases, the sort of you know, rare events. I guess it's hard to train on those to sort of develop the neural network. How do you have you looked into sort of these rare events or sort of extreme cases?
The problem with the rare, okay, so I think this is one problem I still don't really know how to get around, which is generating the data. So like me as a non-system operator, I don't have the real, you know, full fidelity data. All of the grids in the US are private. We have synthetic representations of them, but all of them are private, and there's no way to get around that. So what I've been doing is using these IEEE test cases. I pick a random load within, like, you know, 50% of the base loading case. It just randomly samples. It sends it to a map power solver, and if it solves successfully, I store the point. But a lot of times this solver can't solve successfully. So there's no guarantee that point was actually infeasible. It's just like, oh, the solver struggled. So they're probably in these rare event cases, which are usually close to like voltage collapse or the system being extremely heavily loaded, the solver can't even solve it. So those points aren't generated for my training set. So that's, I still don't know exactly how to get around that problem of generating the training data.
That's interesting. Okay, so I think that's all our questions. I recommend looking at Kyri's website. There's lots of interesting papers on there. I understand you're also welcome to take some questions if anyone emails you. If you have any other further question follow-ups, and we'll record this anyway so people can play it back and watch later. And so if there's nothing else, I just want to thank Kyri for giving this brilliant talk today. And yeah, so thanks all for coming.